Okay, class, I think we can start now. Okay, so for first one, we have showed that integrate this x times x minus 2 to the power 3 over 2 is equals to given the expression here. So first, how do we do this is we will let u to be x minus 2. And from there, we know that if we actually use the substitution, we need to use a du is equals to dx because we have differentiated the u with respect to x here. Okay, and then also we know that for this one, okay, we actually have the x. Okay, if we make that as a subject, we'll actually have x is equals to u plus 2 from there. Okay, so after that is to substitute, okay, all the terms inside our integral. So we have got first one is we have got x. Okay, x here is u plus 2, okay, as what we had before. And also we have got the x minus 2. Okay, so the x minus 2 is given as the u lah. Okay, it's based on we make the u to be x minus 2 as a substitution. Okay, and after that is we just need to expand because we do not know how to integrate this straight away. So from there we have to we just have to expand from there. And by expanding, okay, we actually have two terms which it's very easy for us to integrate from there lah. So it's u power 5 over 2 and 2u power 3 over 2. Okay, so that's there are the two terms that we can actually integrate easily. And after that we have got integrated. Okay, we have got like this, which we have distance, we have got 2 over 7 u power 7 over 2 and also 4 over 5 times u power 5 over 2. Okay, so in that case, how do we actually get something that is required in the result is that, okay, if you look at the result, we have got something which is like x minus 2 to the power of 5 over 2. So for this one, we know that we are going to have something which is we need to have something which is like u to the power of a 5 over 2. So what we can do, okay, in the first thing is just look at the constant that we have here. So for this 2 over 7 and 4 over 5, because in the showing, okay, we need to prove that we have got 2 over 35. Okay, so from there, let's just try to factorize out the 2 over 35, okay, from both terms there. And also we have got x minus 2 to the power of 5 over 2. So that one is actually our u to the power of 5 over 2. So we also factorize out u to the power of 5 over 2 from there. And if we actually do this, okay, the terms that we have in remain is we have got 5u plus 14 from there. Okay, and we know, okay, from there the u here is x minus 2 5 over 2. And in order for us to get another linear term, there is we know that the u is x minus 2. So for this u, we substitute back the x minus 2 inside, carry out a little bit of the calculation, and that is where we can actually get this result, okay, that we need to prove from there lah. Okay, so that's for the first part. Okay, as for the second part, okay, hence find the coordinates of the stationary points of this curve. So we can see that for this curve, right, it is very similar to what we did before. So before this, we know that by integrating this x times x minus 2 to the power of 3 over 2, we know that we are going to get this result. So in our second part here, we have got the similar result. So in this case, we are going to find the stationary point. So it means we are going to differentiate that. So we know that integrating x times x minus 2 to the power of 3 over 2 is going to give us this one. So it means differentiate this thing is going to give us this one. Okay, so that is the first thing that we know. We don't even need to apply any technique from there because they say hence. Okay, so we are supposed to use the result in the previous part. So we still have two other terms from there, okay, which is x plus 2 minus 1 over 3, x power 3. So for that one, we know, okay, how to differentiate from that. Okay, so by considering the result that we have earlier on, so this is what we get, okay, after we differentiate. So we have got dy dx is equals to x times x minus 2 to the power of 3 over 2 plus 2x minus x squared. Okay, so that is the result that we already have. And from there, okay, in order for us to actually, because in this case we want to find the stationary point, so it means we have got like dy dx is equals to 0, okay. So if it actually remain, okay, as this form, it is a little bit difficult to solve. It is when we have like dy dx is equal to 0, okay. It is not to say that it is it cannot be done, okay. When we actually make dy dx equals to 0 and we solve it, it actually can be done, but why don't we just simplify a little bit first before we actually make the dy dx equals to 0. So in that case, okay, what can we do from there is, okay, note that for the 2x minus x squared, if we actually factorize out the negative x from these two terms here, we will actually have the same thing inside, which is the x minus 2. Okay, so for the first term, we have got x times x minus 2 with a certain power. For second term, we also have the similar thing, which is x times x minus 2. So with that, we can actually factorize the x minus 2 out, okay, which gives this, okay, x minus 2 to the power of half minus 1. Okay, so that is for our dy dx. Okay, so next on is to find the stationary point. So for stationary point, we have got dy dx is equal to 0, and from there just make each of the terms here to be equal to 0. Okay, so for the first one, we have got x equals to 0. So for this one, we are going to reject that. Okay, so why do we reject it? We just have to go back to the question. Okay, so we are going to reject this one is because it is not going to satisfy this equation. So we are going to reject the value from that. Okay, in that case, okay, we will only take the two values where we have got x is equals to 2 and we have x is equals to 3 from that. Okay, so in this case, we cannot take the value which is x is equals to 0. Okay, so the reason, okay, again, what is the reason that we cannot take x is equals to 0? Okay, is we cannot, if you look at this equation here, if you have x is equals to 0, we are trying to find the root. Okay, because this is power 5 over 2 means we are trying to find the square root of a negative 2, then we only power 5 from there. Okay, so this is what I mean by it cannot, the equation is not valid, okay, when we have x is equal to 0. So this is why we need to ignore, okay, or reject the x is equal to 0. Okay, so from there we only have two values of the x. So for each value of the x, we just have to substitute inside the y there, and we'll actually get the values for the y. So with that, we just give out what are the coordinates of the stationary point. Okay, so since the question they say they need the coordinates, okay, of the stationary point, so we really have to give out the write out, okay, the coordinates of the points. Okay, so that's for the first question that we'll look at. So next one, so use integration by parts twice to show that integrating this e power x sine x is equal to this result. So the question is already clear enough. We need to use by part and we need to use it twice. Okay, so so we will actually start with the e power x sine x. So from there, okay, we can because it's by part, so we need to decide which one is our u and which one is our dv. So in my case, right, I actually make the u as e power x and our dv as a sine x. If let's say you actually change the order, say if you use u is equals to sine x and dv is equals to e power x, it will actually gives us the similar result. Okay, so don't worry, there's no definite rule in this case to choose e power x or sine x as our u. Okay, it's free for you to choose any order in this case. We will actually end up with the same result. Okay, so let's say if you actually make u to be e power x in this case and our dv is sine x, so from there the u we need to differentiate, we get e power x. Okay, and for the dv, when we integrate, we get negative cos x. Okay, so from there we just have to use the by parts. So we have got uv, this is minus v du. Okay, so from there, okay, we will actually have the first one is just as like this. Okay, so for the second one here, we need to integrate this one, which is e power x cos x. So for this e power x cos x, we need to use by part again. So if we use by part in this case, I'm making the e power x in this case as a u again, which will actually result in e power x for our du. And for cos x, we'll make it as a dv, and then in this case, our v will be sin x. Okay, and with that, just do another round of by part. So we have uv, this is uv minus v du. Okay, so in this case, we actually see that the left hand side we have integrate e power x sin x, and in our right hand side here we also have another same term, but it is a negative term. So what can we do is we can actually move this over, okay, to become 2 of the integrate e power x sin x. Okay, and our right hand side we only have a e power x, we factorize out, and then we have got sin x minus cos x, okay, for our right hand side from there. So after that, it's just we have to move the 2 over, okay, to get a half here, and then because this is an indefinite integral, so no matter what is our working in the middle, at last we must always include the constant to it, okay, because this is an indefinite integral. Okay, so that will be our part 1. Okay, part 2. Hence, find the equation of the curve which passes through the point 0, 2, and for which the dy dx is equal to e power x sin x. So for the part 2 that we have here, we are given dy dx, and we are supposed to find what is a y. So from dy dx, okay, if you want to find y, it means we need to integrate this, okay, e power x sin x. So y here is just integrate e power x sin x, okay, which will actually gives us this result. And whenever we are trying to find the equation of the curve, because we are trying to integrate the dy dx, so when we actually integrate anything, we will actually have a constant. Okay, so for the constant that we have here, we are given the value. Okay, this curve passes through the point which is 0, 2. So we need to substitute the x equals to 0 and y is equals to 2 in this case to actually gives the constant. Okay, we need to find out what is this constant here. So by working out the constant, we actually have the constant as 5 over 2. So basically just substitute back, okay, what is the constant from there. Okay, so that would be the second part for this question. Alright. Next one. So by using the substitution where we have u is equal to 3 minus 2x, okay, or otherwise show that we have got this integral is equal to this number, okay, and it's a 7 marks question. Alright, so of course the u is already given, okay, as a 3 minus 2x, and it's a substitution, so we know we are going to differentiate the u, then we will get du dx. So in that case, our du dx is negative 2 dx, and our dx, okay, if we rearrange a little bit, okay, we'll actually get negative half a du. Okay, so from there, whenever we have the substitution, remember to change the values, because the values given in the integral earlier is 0 and 1, so we need to change, okay, the value to be the u. So in that case, the corresponding value for the u will be 3 and 1. Okay, so next one is we have got this integral, okay, and we need to replace all the x there to be u. So you can first expand it, okay, to be for us to be easier to do our work. So in that case, what we actually have is we have got, okay, so we have got, in this case, we have got dx. So the dx is negative half du. Okay, so that is what we have from there. And for our numerator is just a u squared. Okay, so it is actually quite clear from there as well. So for the numerator, we have got 16x squared. So we have to manipulate with this relationship until we get a 16x squared. Okay, so if we actually manipulate this one, we will get 2x is equal to 3 minus u. And then we can square that. So if we square that, we get 4x squared is equals to 3 minus u squared. But here we need a 16. So we still have to times a 4. Okay, so this is why we get 16x squared is equals to 4 times 3 minus u, the whole thing squared. Okay, so this is why we actually get this numerator here. Just have to manipulate the expressions given in the substitution. Okay, so there are several ways that we can actually do this, but because what we have in our denominator is in our denominator, okay, we only have one single term, which is u squared. Okay, and for our numerator we have got like 3 minus u squared. So in that case, what we can actually do is we can actually expand, okay, and we can actually separate the terms. So what we have is we have from the second line to the third line, we have got 4 times a negative half, and then we will actually get, okay, from here, let me write down slowly. So from there we actually get a negative 2, 3 to 1, okay, and then we have got 3 minus u divided by u squared du. Because this is squared and squared, so we can actually factorize the square out and write them in a single term. So in the next slide, we will see that the limit changes the order. So this is when we have a negative, we can actually change the order for the limit. So this is why the negative is no more there. Okay, there's no more negative here, but in this case the limit has already changed, okay, as compared to what we have in the previous part. Okay, so inside here we have got 3 minus u over u, the whole thing squared, which can be written in this form. We actually split the terms first in order for us to integrate easier, and from there we expand, okay, because this one we know how to expand it easily, and after we expand, we know that we can actually integrate them, okay, for all the terms there. So for the terms there, we have got 9 over u squared, okay, for the first one, and we have negative 6 over u plus 1. Okay, so integrate each one carefully. So integrate 1, we get a u. Integrate 6 over u, we get 6 ln u. Okay, for the first term, okay, 9 over u squared, when we integrate is negative 9 over u. Use the power of the u to integrate, not the ln. Okay, ln can only be used when we have a linear, okay, in the denominator. Okay, so after that is substituting all the values in, okay, to the integral that we have actually obtained. Okay, so by tidying up the values, you will actually have the value that is required, okay, as the proof. Okay, so that's for the part 1. Second part is we have got the region R, which is bounded by the curve y is equals to 4x divided by 3 over 2x. Y is equals to 4 and the y-axis. And find the exact volume generated when the region R is rotated completely around the x-axis. Okay, so for this one, what are they actually looking at is they are actually looking at this region, okay, which we have to generate, okay, when we revolve around the x-axis. Okay, so for this volume, it is definitely not the pi y squared only. So it is definitely not pi integrate y squared. Okay, so if we actually do this, it means we are actually looking for this one here. So this one is here. The R is not this one, so this is not our R. Okay, so from there, what we need to do is we need to actually find out the volume for the whole thing here, and then we have to minus out this part, okay, which is below the curve, in order for us to get the volume generated, which is by this area here. Okay, so what we need to do is we need to find the area, or sorry, rather the volume for the 4 minus off the volume for this. Okay, so from there, what we actually have is when in this case we are actually looking at, again, another thing is we want to know what is this value here. Okay, so this value is a 1. So how do we do that is, because we know here the y is equals to 4, so we just have to substitute 4 here, and we can actually solve for the x. Okay, so the x is a 1. Okay, so we actually integrate this expression from 0 to 1. Okay, so we can actually look at the working later here. So x is equals to 1. Okay, and from there we actually have to use the pi y1 squared minus y2 squared dx. So in that case, the y1 is the curve which is above, okay, the higher curve. So the higher curve in our case is the 4. Okay, this is our y value. So this is why we have got 4 square, which is this one. And for this one is the under the curve. This one, but under the curve. Okay, so we have got this one. So earlier on, we already know for this part, okay, we already know the result because what we did earlier on was we also integrated this from 0 to 1. Okay, so we already know the result, just quote the result from the previous part. And for this one, okay, we have got 16, so we have to integrate the 16, so we get a 16x, and just substitute the 1 and 0 and calculate. Okay, so working out the values carefully, we will actually get this volume. Okay, so it's by using the result that we have got earlier on. Alright. So we'll also look at the next question. Okay, so next question. Okay, so the diagram shows parts of the curve which we are given for this equation of the curve. Okay, where k is a constant greater than 0, so it's a positive constant. The curve has stationary point at x equals to 0, and this is a local minimum. So show that there are no other stationary points. So whenever they talk about stationary points, we know very well, okay, we are going to use dy dx in this case. So for the dy dx, okay, it is easier for us if we actually move the denominator up and then we differentiate from there. So 1 over the whole thing squared become the thing inside, and we have the power -2 from here, and then it is easier for us to do the differentiation from there. Okay, so when we actually do the differentiation, we have got the power -2, we need to multiply. So the power will -1, okay, we'll get -3 for the power. And then we also need to look at inside the bracket, okay, then we have to differentiate it. So k squared is a constant, x squared when we differentiate we get a 2x, okay, and then when we actually tidy up, this is what we get. Okay, and now we're actually looking at the stationary point. So in this case, we are looking at dy dx is equals to 0. So in this case, when dy dx equals to 0, the only thing that we have is we look at the numerator. So the numerator, which is -4x, is equals to 0. So there is only one value that gives us which is x is equals to 0. So from there, it is already proven. This is the only stationary point that we have for this curve. Okay, so that will be for the first part. So next one. So using the substitution x equals to k tangent u to show that we have got this integral is equals to the expression here. Okay, so if we start with the substitution where we have x is equals to k tangent u, so in this case we need to find the dx du. So we have dx is equals to k secant squared du. So we know differentiate tangent, we get a secant squared from there. And we have in the integral we have got 0 and k for our values of x, okay, as the limit. So now since we already expressing them in terms of u, we need to change the value to the u. So when x equals to 0, our u is equals to 0, use this relationship. And when x equals to k, we have got u is equals to pi over 4. Okay, so that is what we do when we change the value from the x to u in this case. Okay, so now we actually start integrating. So when we integrate, we have got this is our integral, and limits we have already changed them. So dx, okay, dx is what we have here. So we have k secant squared, and then also we have got the du here, and also we have got the x here, right? So the x, we just have to substitute the k tangent inside. Okay. So after that is about to tidy up the stuff a little bit. So for this one, okay, for the denominator, we see we have got k squared right in the bracket, and then this bracket has a square. Okay, so when we actually factorize the k squared out, the k squared would bring together with the square, which will result in k power 4. Okay, so inside we have tangent 1 plus tangent squared u, the whole thing squared. So 1 plus tangent squared u is a secant squared. Okay, so inside the bracket is a secant squared, so we square that again, we get a secant power 4. Okay, and for the constant k and the k power 4, we cancel them out, we will only have 1 over k power 3, and then we just leave that outside. So from this, okay, what we get is we get 1 over secant squared, which is just a cos squared. Okay, so here we need to integrate the cos squared. So again, like what we did yesterday, we know that sine squared, cos squared, tangent squared, they cannot be integrated directly. So for cos squared, we need to use the double angle formula. Okay, so we used cos 2u is equals to 2 cos squared u minus 1. Okay, and we will actually reach this identity. Okay, so for this one, we know we can actually integrate straight away from there already. So we have got half cos 2u, integrate we get 1 over 4 sine 2u, and half we will actually get half u from there. Okay, and we substitute the values in, we have got pi over 4 and 0, and calculate the values. Okay, and then for this one, we actually have 1 over 4 plus pi over 8, and then for this case, it is just we have to combine the two fractions together, and in order for us to get a single fraction from that. Okay, so this is what we need to prove for the part 2. Okay, so that's for our part 2. Okay, if we look at the question for part 3 again. So for part 3, we have got hence find the area enclosed by the curve y is equals to this one. The tangent to the curve at x equals to 0 and the line which is x is equals to k. Okay, so if you actually look at the question here, so they are actually looking for the area, okay, enclosed by this curve. The tangent to the curve at x equals to 0 and line x is equals to k. So what do we have from there? So this is the tangent line, okay, when we have x is equals to 0. And then we also have another line which is when x is equals to k. So what are they looking at is basically the region or the area that we're looking at is this one. Okay, and then we know that for this, okay, when we have x equals to 0, in this case, we will actually have the y value here is a 1 over k power 4. This is our y value. Okay, so it's this region, not this one. Okay, so how do we actually get the area for this region is we already have the result for this one. Okay, area under the curve from 0 to k is already given here. Okay, so basically we just have to use the area of this rectangle here. So the area of this rectangle is given by base times height. So the area of this rectangle here is 1 over k power 3. Okay, so we use 1 over k power 3 from there, okay, to minus off, okay, the area that we have shown in part B, and in that case we can actually get the value. Okay, just combine these two fractions as a single fraction and we'll actually get the area which is given by this expression. Okay, alright, so basically that is it for all the exercise for the integration. So I will see you tomorrow for another session. Okay, thank you.